Hi, grade 12. Today we want to talk more about electric fields and more specifically the electric field strength. Now I'm going to be trying to make a lot of comparisons in this section, chapter 7 of our textbook, to gravitational fields because we're more familiar with them thanks to grade 11 physics. And that's why the format of this first page looks an awful lot like that chapter 6 summary that I gave you, and that's because I modeled it after what I had created there. Now, what we can see up here at the top is the electric field around a negative charge and a positive charge. Now, we can tell that this charge here is negative and that this charge here is positive because of the direction of these blue field lines. So remember that electric field is going to follow the direction of a positive test charge, which is towards a negative and away from a positive. Now that means if this little charge here was positive, for example, it would be attracted to this central charge and take on that direction, and if it was positive here, it would be repelled from this one. So that's how we can figure out the direction of these field lines as well as these ones over here, just by figuring out which way that charge would move if it were positive. Now, these electric fields, which is what these blue arrows are modeling, are created because of charge, and they're going to affect charge. Now, there's a little asterisk here because there is some stuff that we're going to talk about when we get to chapter 8 with magnets, but we're not there yet. Now, if we want to calculate the magnitude of the electric force within this field, so I'll say this little green arrow here or here, we could figure out the magnitude by using Coulomb's law. Now, Coulomb's law is written down here for us. It's just that Fe equals K QQ over R squared. And when we're applying this formula, we want to make sure that we're using the magnitudes of the charges only. So if you need to, you can write in those absolute value signs to make sure that you're really emphasizing that for yourself. Now, this should look really familiar to what we did before with Newton's universal law of gravitation, which looked something like this. Okay, so we're following a very similar pattern. Now, when we were looking at gravity, we did have a second way that we were able to calculate the force of gravity, and that was Fg equals mg. So we could figure out the force of gravity at some point if we knew the object's mass that's within that gravitational field, as well as the gravitational field strength. Now, this gravitational field strength was technically a vector quantity, as was this force right here. Now, following that pattern, we can come up with a second formula to determine the electric force. And since mass is similar to charge, we've got the gravitational field, which will be similar to something new here represented by this character epsilon. That is the electric field strength. Now, the electric field strength is technically a vector quantity, so we could write it as a vector there, and then get our vector arrow over here as well for that electric force. Or if you're comfortable applying the law of electric charges, you can continue to do that. Now, what is the electric field strength? Well, the gravitational field strength, little g, tells us how many newtons of force every unit of mass would experience at a specific point. And the electric field strength is the same idea, just with charges instead of mass. So it's a quantity that tells us how much force every unit of charge would experience. So I've written an example down here for us. Right here. So if we had an electric field strength of 3.2 newtons per coulomb, it means that 1 coulomb of charge would experience 3.2 newtons of force at that point in space. Now, I've given us a model of this up here with these concentric dashed circles. Now, what this is showing us is regions of space where the electric field strength would be constant. So At any point along this dashed line, the electric field strength would be constant. At any point along this dashed line, the electric field strength would be constant. But the electric field strength along this line is different than the electric field strength along here, just like we saw with gravitational field strength back in chapter 6. Now, what can we take away from this shape of these concentric circles? Well, we can see that as long as the charge remains the same and our distance from the charge remains the same, hence this circular shape, our electric field strength will remain the same. So if we wanted to quantify the electric field strength, we need something that's going to represent that central charge as well as represent that separation from it, that radius. So we can take our two different equations for electric force, the magnitudes of them, and set them equal to one another. This is the same thing we did when we were looking at the gravitational field strength. Now, this lowercase q, this is the one that represents the secondary charge I've placed within that field, is going to cancel out, and we're left with the magnitude of the electric field strength. I'll just write that over there. The magnitude of our electric field strength is equal to that constant times our charge of the object creating that electric field divided by the square of our distance from its center. So that's what our formula is going to look like. And that's actually already typed out for you if you did print out your notes. Now, it's important to note that this epsilon character is a vector quantity. It will have a direction associated with it. So that is expected for you to include in your answers to any of these questions. The direction of the electric field strength is the same as the direction of the field lines, meaning that it's going to point in whichever direction a positive charge would move. So if you were to put a positive charge at whatever point in space you're analyzing, whichever way that positive charge would move, that's the direction you give to your electric field strength vector. Now that might sound like a bunch of gibberish. We're going to try to go through it in an example and see if we can't get it to make more sense. All right, so in this first example, we've got a 3.6 nanocoulomb charge. Now, nano just means times 10 to the negative 9. So that's all this is saying. And it's going to be placed in some open space free from other charges. Now I've got a diagram of this here below, and what we're going to do is we're going to figure out the electric field strength at a point 15 centimeters to the right of that charge. Now diagrams are your friend. In it's physics, diagrams are always your friend, but you may want to draw them in here for yourself. So I'm going to draw some diagrams to represent the electric field, and then I'll show you what those concentric circles might look like. So we know electric field is going to be occurring radially, and the electric field points the exact same way that a positive test charge would want to move. A positive test charge would want to get away from another positive charge. So your electric field points away from a positive charge. Now these arrows are also telling me the direction that my electric field strength is going to take on. So the electric field strength is just these sort of dashed lines that we had in that previous picture. Now we're not really concerned about them out there. We're concerned about what's going on where this X is. So we're trying to calculate epsilon sort of right at this X, right along this point that we're at. Now, if we want to calculate the magnitude of the electric field strength, we can use K, Q over R squared. Remember, K is that new constant. You can write it out if you'd like to. Q is still just going to represent the magnitude of the charge, in this case, the magnitude of the charge of the object in the middle here. If you need to write absolute value signs to remind yourself of that, go ahead. although it's not really necessary in this case because we do have a positive charge. And then we're going to divide that by how far we are from the object creating the charge. In this case, that was given to us in centimeters. You want to make sure that you convert that to meters first. Okay, and then just off to the side here, we'll figure out what epsilon is. So we're going to get about 1.4 times 10 to the 3 newtons per coulomb. Now, if the question is worded this way, and it just says to calculate the electric field strength, it doesn't specify the magnitude only, you want to make sure you give that electric field strength with a direction. Now, in this case, we'll just look back at our diagram. The direction is the same direction as these field lines, which would be away from that charge. So I'm just going to say towards the right here. So that's what we're looking at. Now, hopefully that wasn't too bad, because we are going to try and use our answer from that one for part B. Now, part B is asking, what would be the force if instead of having some mystery point X at that space, we actually put a charge and we put it there. So we're going to replace this X with a charge of 2 nanocoulombs. Now we want to figure out what is the force on this positive charge. Now you can probably already tell by looking at it, if you've got a positive charge and a positive charge, it's going to move away. So we're being asked to figure out the magnitude of that force as well as the direction. Now you've got 2 options here to figure out what that force is. Option 1 is to use Coulomb's law. So you could go ahead and use this formula and then use the law of electric charges to confirm that direction, which we've already done. Your second option is to use that number that we just calculated. So we know that Fe equals Q epsilon. Now we've already done the work to figure out what epsilon is. We know what our charge is. And because this is a positive charge, it's going to experience a force in the direction we've already defined here. So that's kind of a neat trick for using this equation, is that you can actually substitute, if you'd like to, the entire charge with its positive or negative sign in here. And as long as this has the correct direction, your result will have the correct direction as well. So let's see, we've got our 2 nanocoulomb charge, and we're going to multiply that by, I'm just going to grab the unrounded value, 1,438 newtons per coulomb. And this is going to give us about the same idea here. If we wanted to round, 2.8. So the per coulomb is gone because we've multiplied it by coulombs, and we're left with newtons, and our direction would be towards the right, which we can either use the law of electric charges for or the direction from our electric field strength. Now, in the last question here, I just want to discuss how the electric field strength would change if that initial charge that created it changed. So this question is saying, instead of having a positive 3.6 nanocoulomb charge, what would things look like if we had a negative 3.6 nanocoulomb charge? And for some of you, this might seem obvious. For some of you, it might not. Just be where you're at. Don't try to